Good morning, good afternoon, or good evening, depending on where you are in the world, and welcome to part 3 of this week's EETimes University course, Designing for Next Generation Automotive Lighting Requirements, brought to you by EETimes on Semiconductor and broadcast by AspenCore. I'm Patrick Mannion, and I'll be your moderator. As you recall, in part 1, we provided an introduction to automotive lighting. Yesterday, in part 2, we looked closely at choosing a lighting option, and now today, in part 3, we look at designing with LEDs. However, before we begin, I have just a few announcements to make to help you navigate the interface and get the most out of your time. The slides will advance automatically throughout the event. You may also download a copy of the slides by clicking on the green folder icon located at the bottom of your screen. You can participate in the Q&A session by asking questions at any time during the webinar. Just type your question into the Q&A text area located to the right of the presentation window and then click the Submit button. At this time, we recommend you disable all your pop-up blockers. At the end of today's session, we'll ask you to complete our feedback form. Your feedback will provide us with valuable information on how we can improve future events. You can also launch the survey at any time by clicking on the red survey button at the bottom of the console. If you're experiencing any technical problems, please type your issue into the Q&A text area, and we will be glad to offer one-on-one assistance. So now on to part 3 of this week's course, Designing with LEDs. Our lecturer today is Paul Pickering, Senior Analyst at Informa Tech. Paul has been covering developments in the industrial semiconductor market and has over 35 years of engineering and marketing experience, including stints at Automotive Electronics, Precision Analog, Power Semiconductors, Flight Simulation, and Robotics. It's with great pleasure I now turn the special session over to Paul. So Paul, over to you. Take it away.
Thanks very much, Patrick. As Patrick said, good morning, good afternoon, or good evening to everybody. This is part 3 of our discussion of automotive lighting, designed for next-gen automotive lighting requirements. You should be very familiar with me by now, so I'm going to skip quickly over this slide to the next one. This it actually says part 2 overview. It should actually say part 3 overview. I'll fire the editor whenever I get around to meeting him. Part 1, as Patrick said, we talked about history of automotive lighting, some fundamental regulations and standards. Part 2, we talked about some of the basic top-level architectures for front, rear, interior, and instrument cluster, and touched on some related technologies and emerging technologies, what we can expect to see over the next several years. If you recall from day one, automotive lighting certainly in the last 20 years, although it's been around for 130 years, there's been a lot of activity with the development of new technologies and the development of electric vehicles and so on. They are all leading to a lot of change, a lot of improvements in the old standard automotive light, which for many years used to be a switch, a battery, and just a lamp. Very straightforward. Those days are gone. So today we're going to talk about LEDs in more detail, talk about the technology, what is an LED, how does it work, how do we operate it in an automotive lighting environment, what are some of the control options for the designer, how does it fail, how do we package it, and look at some typical devices designed specifically for this application. Finally, we'll touch again on what's next for the LEDs themselves. Okay, so let's get busy. In this section, we're going to concentrate on LEDs, as we said, because they are the most becoming the dominant lighting source in automobiles. And as I said already, there is a lot of development, both the devices themselves and how they're being used in the vehicle. Here you can see some examples of high current LEDs used in automotive. You can see there are a lot of different ways to package these devices, including the one there on the bottom left, which includes an optical element too. It's not just simply an LED. You can see it has the lens to provide some focusing of the LED output. Let's dive right into the physics of an LED. I don't know how many people on the call are engineers, but the LED is a semiconductor device, and it's essentially a diode, except it emits light. When it's forward biased, as you can see here, electrons recombine with holes in the device, and they release energy. And the energy is in the form of photons. This phenomenon is known as electroluminescence. The energy, luckily for us, is released at a constant wavelength, which determines the color of the LED. And the wavelength of the photon is determined by the difference in energy between the two states here. You can see the conduction level and the valence band and the band gap, the forbidden band. The difference between these two determines the light of the LED. Now, normally, diodes have a forward voltage of about 0.65 volts, normal silicon diode. LED, however, has a voltage drop of around 2 volts or higher, and this depends on the wavelength of the color of the light that it emits. The other thing to remember about LEDs is that their brightness is proportional to the forward current. So that means that a mechanism to limit the current is a key part of the design, because if you exceed the forward current, it has a range of undesirable effects on the operation of the LED. We'll talk about this later when we look at various LED control circuits. Here are some of the key LED specifications. Of course, you'll find a lot more specifications in an LED data sheet, such as maximum voltage, current, some notes about ESD capability, but we're going to talk about a few that are particularly important to the automotive lighting application. Let's start with the light output. We defined a luminous flux, which is another word for light output in day one. For an LED, the light output is approximately a linear function of the forward current. It also varies with other parameters, such as case temperature, and declines slowly over the lifetime of the device. So the LED slowly degrades with age. Many LED manufacturers offer devices in different grades, what's called binning. They sort these by luminous flux. So, for example, a particular bin may contain a device, devices that are specified to give an output between 1,000 and 1,100 lumens, for example, under these specified test conditions, whatever is specified in the data sheet. The next specification is maximum operating temperature. This is extremely important because the hotter the LED gets, the worse it performs. Certainly, actually, both in terms of light output and operating life. So if you operate an LED consistently at maximum operating temperature, you can expect to see the light output degrade and the operating life reduce considerably. Conversely, operating below the maximum level has a dramatic effect in the opposite direction. So the light output will increase and the LED will last longer. Thermal resistance is another key specification, not only for LEDs, but for pretty much any power semiconductor. This is defined as the rise in temperature of a component per unit of power dissipated. Typically, it's expressed in degrees C per watt. For an LED, and again for any semiconductor device, the total thermal resistance is not just a function of the semiconductor itself. It includes each individual component within the IC, such as the package is the big one, the leads, even the epoxy, and the bond wires, and so on. So all of those are included, and it's an additive function. All of those are included in the total thermal resistance of the device. For an LED, 1 degree C per watt is a typical number you can use just to give you an idea of what we're talking about. Color temperature, we mentioned this on day one. It's defined in terms of a black body radiator, and the LED color temperature varies with a number of parameters, including case temperature and even viewing angle, and of course, device aging. Now, the automotive market is a pretty difficult one for manufacturers. We mentioned this again earlier in the course. the AEC Q100 series of documents define testing and qualification for electronic components for automotive use to make sure that they're suitable for use in the automotive environment, which is not friendly to electronics. We have extremes of temperature, we have vibration, we have thermal shock, we have a reverse battery. We talked to some of these things before, and so the AEC Q100 product specifications are defined in order that manufacturers can test these, and they go inside the construction of the IC to cover things such as wire bond strength testing, gate leakage, robustness to ESD pulses, and so on. And automotive companies test these parts to give a high degree of confidence that the parts will last for extended period. We're talking 10 to 20-year application life. Contrast that with the life of a typical cell phone, and you'll see that automotive products are pretty tough for manufacturers to meet. Finally, operational life. The primary characteristic that determines this, as we said, the light of an LED slowly declines over time. And that is at some point it reaches the point where we say, well, this LED is no longer emitting enough light to do the job. We talked a little bit about some of the SAE specifications that talk about LED operation in automobiles. SAE J2650, for example, specifies the operational life in terms of the number of hours that the LEDs can maintain a minimum, typically 80% of their initial output. And because this is a statistical metric, the number is specified in percentages and confidence level. So, for example, a specification may say something like, after 15,000 hours, 50% of the devices will still give 80% output at a 90% confidence level. It's a complex specification, but they have tables specifying the performance of these LEDs over different operating lives. Another thing we talked about earlier was what constitutes white, and LEDs go back a long way. They date back to the 1960s. The first LEDs that we saw emitted infrared, actually, closely followed by LEDs that emitted red, green, and yellow. And they've all been around for a long, long time, decades. But to produce white light, of course, we need blue. But a blue LED proved to be a pretty difficult task. And so the first blue LEDs that came out weren't actually LEDs at all, but they were actually small incandescent bulbs surrounded by a blue diffuser to give a blue output. The first semiconductor devices used silicon carbon substrate, but they were very poor in terms of efficiency. And successive generations of devices improved the efficiency tremendously by switching to gallium nitride as the substrate. First high brightness blue LED didn't come around until 1994. And this was such a major breakthrough. 3 Japanese scientists won the Nobel Prize for Physics in 2014 for developing it. So what we see is that current generation white LEDs use a blue emitting material overlaid with a yellow phosphor, and this resulting mixture of blue and yellow is seen by the eye as white. And you can see here there are 2 peaks to the white LED output. The first one is blue, and then the second one is the broader peak corresponds to the maximum sensitivity of the eye. And the human eye relative sensitivity is superimposed there, so you can see what we're talking about. So the dominant wavelength of a blue LED, as you can see here, changes with the forward current. And this change in forward current, if you remember day one, we talked about the CIE chromaticity diagram. This moves the point on the XY coordinates of the point on the chromaticity diagram. And as you can see, those here shows you that as the current changes, the quality of the white light, even though it still appears white, it may have a slightly different tinge to it, which means that, of course, it's even more important for us to control the forward current of an LED. Since we're talking about LED control, let's go over some of the main ways that people use to control an LED, not only in automotive lighting, but indeed in any similar application. So we've seen already that the current must be limited. Simplest way to limit the current is to use a resistor. But a resistor, by its nature, can only act as a current limiter, as a passive device. It's not a current control circuit. This is a simple example of a schematic showing how a resistor is used to control an LED string. As you can see here, 3 LEDs in series. We'll note that this type of circuit, the resistor has to dissipate significant power, especially as battery voltages increase. So it must be a power device, which of course is expensive, and dissipating power as heat involves lots of issues with regard to thermal management. Advantages, of course, is it's a simpler solution. It doesn't get much simpler than a resistor. As we already said, some of the disadvantages include a high power loss across the LED resistor. And so we must define resistor, of course, for the maximum V battery, not the typical operating conditions. And certainly in an internal combustion vehicle with a 12-volt battery, it's quite likely that you might get up to 24 volts under jump start conditions, and even 16 volts during operating. So you need to size it considerably greater than for operation considerably above the standard 12-volt battery. Also, it doesn't have any protections against, for example, overvoltage. So that system is cheap, but not particularly effective. The next system that people have developed is a linear system still, but this has a linear current control. A linear current source, as you see here in the LED module, provides a constant output current to the string, regardless of variations in battery voltage. And most sources of this type include various diagnostic functions. We'll talk a little bit about these later on. These include open and short circuit detection and potentially features such as PWM dimming control. The advantages are that because it's constant current, the brightness is stable, even during situations where the battery, you might think, will vary considerably, such as cold starts and start-stop operation. The LED doesn't degrade over time in the same way because the current is constant and controlled, and we can provide various protections in the current source module itself. Disadvantages, just like we had power dissipation across the resistor, we also potentially have a high power loss across the constant current source. More complicated, so we have increased component count, and it only accommodates a limited LED chain length, which depends on the forward voltage of the individual LEDs, especially when they are in series, as we see here. So moving up the scale of complexity and capability, we're now moving from a linear control solution to a switched control solution. DC-DC converter is a switched mode topology for supplying power to the LED. And switched mode topologies have some well-known advantages and well-known disadvantages. They're used very widely in all areas of power conversion. from power supplies on down. The advantages are, in general, that the DC to DC solution or switching solution has much higher efficiency than the linear solution. If you saw the last two versions, we had components whose function, one of whose functions was to dissipate a large amount of power through the device, which meant that that power was wasted. A DC to DC converter, broadly speaking, does not suffer from that problem. So it's the highest efficiency. On the other hand, it achieves this efficiency through a switching means, and the switching control scheme has the disadvantage of generating a lot of noise and EMI and so on, and that is a problem for other sensitive electronic components. So the design has to take extra care to minimize the effects of the noise and, in fact, the generation of the noise itself. There are a choice of DC to DC converter topologies, and depending on such things as the supply voltage range and the number of LEDs that you're driving in the string, and of course, typically DC to DC converters these days are integrated devices with a large amount of functionality that includes diagnostic functions. And you see here, briefly, we summarize some of the advantages and disadvantages. But nonetheless, it's a more effective way to control an LED than some of the linear systems that we looked at before. The final version that we will discuss is the DC to DC converter plus a linear constant current control, which in a sense provides the best of both worlds, but at the cost of an even more increased component count. And this is very useful if we have, for example, multiple LED strings combined into a matrix lighting arrangement, which we talked about and we'll talk about more later on, where we have individual LED strings that are turned on and off in real time to accomplish various functions, in particular forming the beam to avoid dazzling oncoming drivers. This control scheme combines a DC to DC converter working in a constant voltage mode together with one or more linear current sources, one for each string. So the DC to DC converter in this application provides an output voltage that's optimized for the LED string length, and then the output voltage is converted into a constant output current by the linear current sources. And this gives us more efficient LED control. But again, it's the most expensive solution with increased component count versus all of the others. And once again, because it essentially starts with a switched topology, we have to worry about EMC, electrical noise. And so the PC board layout must be optimized with a view to keeping sensitive circuitry that's susceptible to electromagnetic interference away from the switching circuitry. And if you go to any of the mainstream semiconductor companies' websites, you will find many application notes talking specifically about this problem, how to deal with switched transients and how to optimize your PC board layout in order to minimize the effects on the rest of the circuitry. We talked a little bit earlier about failure modes. And as I said, the dominant cause of LED failure is simply a gradual lowering of the light output and loss of efficiency. But having said that, it's possible that the LED can suffer a sudden catastrophic failure, even though these are actually relatively rare. So if we look at some of these failures, catastrophic failures, there are basically three main categories related to packaging, thermal stress, or a degradation of the epoxy or the phosphor or other packaging components. Common sources of these stress-related failures are such things as thermal runaway, ESD pulses, or even reverse bias if you exceed the reverse breakdown voltage of the LEDs, which is only about 5 volts for an LED compared to a much higher level for a standard silicon diode. Also, there are a number of failures related to the semiconductor operation itself, such things as dislocations due to crystal defects, concepts such as electromigration, metal diffusion caused by metal whiskers, which form on the die when it undergoes stress or high currents, effects due to such things as ionizing radiation and so on. And these are all very specialized things that we won't really discuss here, but you can go again to any of the semiconductor company sites and you can see discussions in the quality and reliability section about failure mechanisms such as this. And I would encourage you to take a look at those if you're interested. So once the LEDs failed, clearly we need to detect the failure, and this falls in the area of LED diagnostics. So catastrophic failures really are of 2 types. We already talked about the slow degradation, which is a completely different issue. But there are 2 basically catastrophic failures. We'll give you an open circuit or a short circuit. And this must be detected for a number of reasons. We need to alert the driver if it's not obvious, for instance, because the headlight turns off. And also ISO 26262, as we mentioned, does mandate graceful degradation and detection and diagnosis of some of these failures. So given that we have a constant current drive, an open circuit will cause a current to fall to 0, which of course is easily detected. The effect of an LED short, though, is not quite as straightforward. The detection of that depends on the drive circuit. So if an LED in a string shorts out, the voltage will go to 0 across that LED, and then that can be detected by the circuitry. That may not be that easy to do because LEDs, even with modern quality control techniques, do have slightly different forward voltages. And in an LED in a long series string, it may not be obvious that one of the LEDs has gone to 0. Sometimes manufacturers will measure the forward voltage and indicate that on the LED, sometimes even stored in a barcode. And then a microcontroller controlling strings of LEDs can store those in memory, and then that will give it an idea of what it expects to see for the forward voltage, and use that for comparison to determine whether a failure has occurred. And of course, LED diagnostics now are included in most of the high-functioned, highly integrated control ICs that we'll talk about a little bit later on. We've talked a little bit about packaging, and here are some examples of how manufacturers package LEDs. This particular version is in a 1x4 array, so we have 4 light-emitting die on a single package. Packaging is important because packaging represents up to around about 40% of the total cost. So it doesn't make sense for manufacturers to package individual light-emitting components in their own packages. And as you can see here, they developed a range of solutions for doing this while minimizing the cost. One option is, as you can see, to mount several LEDs in an array. And these are, of course, available in a variety of form factors, including leaded and surface mount packages. And we saw some of the others in this a few slides back, including the one that has the integrated optics. Now, thermal management is another issue that manufacturers need to pay attention to. Even though, as we've seen, LEDs are far more efficient than some of the other options out there, and particularly far more efficient than incandescent bulbs, they still do generate significant heat, which actually may be surprising because they're typically cool to the touch. The light that LEDs emit contains practically no UV or IR, infrared radiation, which means that they're cool to the touch, and they don't heat up. The light from an LED, because it doesn't have UV or IR radiation, does not heat up illuminated objects. But they are not 100% efficient. In fact, up to 85% of the energy consumed is dissipated as heat, but it doesn't come out through the front of the LED. In fact, most of the heat produced by an LED is conducted through the back of the package, on the back of the IC to the heat sink. So it's very important to pay attention to thermal management, especially given the fact that excessive junction temperature, as we've seen, is a major cause of reduced operating life. So manufacturers and circuit board designers need to minimize the total thermal resistance of every stage to give the lowest thermal resistance from the junction to ambient, in other words, the outside environment. This is an example of a data sheet that illustrates the operating life of how the operating life of an LED varies with a different operating temperature. And this B50L80 parameter that you see here is defined as the hours of operation at which the light output of half the LEDs has degraded to 80% of the original value. If you remember, we talked about confidence and so on in an earlier slide. So you can see from this, if you increase the temperature by only 20 degrees, that it reduces the operating life. In fact, a decrease by 20 degrees boosts it by over 260%, even if we maintain the same forward current. And also, of course, we could also lower the forward current, but and that would also reduce the operating life. But that also that has the unfortunate effect of lowering the light output. So it's much better from the manufacturer's point of view to keep the temperature under control to get the most light for the longest period. In order to perform effective thermal management, manufacturers of automobiles have developed several methods. You can see here, and one of those is a heat sink. And another one is a cooling fan. There are other more complicated options too, with various cost convenience trade-offs. For example, heat sink with a heat pipe is another one. And these are a couple of examples, I think, on Audi automobiles of two options for thermal management. So now we are going to take a look at some typical devices from our sponsor on Semiconductor. As we said before, the automotive market and lighting in particular is a key market for semiconductor manufacturers. It's a very large market for many companies. And so as a consequence, they make specialized devices that meet the stringent automotive requirements, which we've discussed various points of this presentation. So we're going to look at 8 different devices here, as you can see here, at various levels of complexity that cover various applications, front lighting, rear lighting, and at the end we'll talk about the newest device, which is a pixel controller that produces is designed to accommodate this pixel lighting application that we've talked about before for these advanced lighting applications. First device we're going to talk about is the NCV 78763. This is a single chip device. It's designed for automotive front lighting applications, high beam, low beam. These include daytime running lights, turn indicators, fog lights, and so on. This is set up to drive 2 LED strings. Forward voltage of the combined string can be up to 60 volts, and it can provide up to 1.6 amps from a standard 12-volt battery, which means it's a switching solution. And so it's highly efficient. So this device includes typical efficiency of up to 94%. It includes PWM dimming, which is under the control of a SPI interface from a controlling microcontroller. And as we mentioned, this is a high-function device. So it includes multiple diagnostic modes, for example, thermal protection, temperature monitoring, and the detection of both open and short circuits. Because the battery is 12 volts in a typical internal combustion vehicle, and because this produces up to 60 volts, this is a boost device. You can see at the top there all of the external components needed to implement the boost function in conjunction with the switching the gate drivers for the power FET at the top there, which is internal to the device. And so standard components in a typical switching solution include an inductor, a switching element, and a diode, which all of this you see at the top. Next device we'll look at is the NCV 78703. This is also a device intended for front lighting applications, designed for high current LEDs, and this one has external power transistors to allow it to drive higher currents than if the transistors were internal to the device. You can cascade 2 of these together. I don't mean cascade, I mean connected in parallel, sorry. You connect 2 of these in parallel together to operate as a multi-phase circuit to lower the application cost if you have a higher power device. And again, this is controlled by the SPI interface, and the multi-phase mode, which is multi-phase power conversion, is a standard technique to reduce ripple current caused by the switching frequencies in the device. And as I said, you combine 2 of these together for that purpose. Now, one of the other things that we can do with LEDs, and we've talked about this specifically with regard to interior lighting, is that we can combine red, green, blue LEDs for multicolor to vary the color applications. And that's what the NCV 7430 is intended to do. This one includes a LIN interface, which you will recall is a low-speed, low-cost serial communications bus that's widely used for a lot of body control functions. So this device receives instructions over the LIN bus and drives each LED independently using a constant current source and programmable maximum current. Also, this includes a fading function. So if we wanted to do something, for instance, theater dimming, we want to change intensities and change color at the same time, this device can do that. And as I mentioned, interior lights are one area in automotive where the designers can give free range of their creativity in terms of colors, intensities, and various features. The NCV 7691 is a simpler device. It's a constant current controller, which we've seen is an integral part of some of these other, some of the control schemes for LEDs. This one is targeted at automotive rear combination lamps or similar applications such as the daytime running lamps or the center high mounted stoplight or chimsel array. And it's a single driver, and designers can add multiple single channel to multi-channel system, or indeed use several of them together for a multi-channel application. And this one also has a dimming feature, but this one is included rather than SPI or LIN. It's included as a PWM into the device. And as I say, this is a simpler device. Brightness levels are programmed using an external resistor in series with resistor with the transistor, as you see here. And this gives you the option to use it over a wide range of currents. And in this application, you can see we have a string of 3 LEDs that are being used. The NSI 45020, this is a constant current regulator. And again, we're no longer talking about automotive headlights. We're talking about some of the lower power applications, such as the side mirror indicators that tell you when your turn signal is on, or instrument backlighting, or again, the chimsel or map lights. It's also available, incidentally, in a non-automotive version. Many of these automotive LED lighting applications have their counterparts in non-automotive applications, and so consequently many of the devices are available in non-automotive versions which do not undergo the stringent automotive qualification. There's no sense in paying for something that you don't need. And display signage, for example, decorative lighting, don't require some of the things that the automotive guys do. So consequently, they make a version available for that. Next device we just want to touch on is NCV 7680. This device is designed for multiple strings of LEDs. This is a common configuration for a rear combination lamp application in a vehicle. This one provides 8 outputs, which allow the driving of 8 individual LED strings with the current set by a resistor. And the output currents are matched in the device to within plus or minus 5% at a hot temperature. And it allows for 2 brightness levels with external resistors also. And for example, they would be used, one for stop and one for tail illumination for a rear light LED array. It also has built-in protections like most of the devices we've talked about. These include current limit, thermal limit, and detection of open LED strings. And there's a diagnostic pin that is used to report the failures that it detects. This is CAV 4201, is a step-down LED driver for high current LEDs. Again, it has an efficiency of up to 94% and has a single resistor to set the full-scale LED current, which can be up to 350 milliamps from a battery supply of up to 36 volts. Again, this is a switching architecture. You can see the external inductor there. It allows it, because switching, as we've said, switching topology is efficient. It allows the device to be housed in a very small package. In this case, it's a TSOT23 without needing a dedicated heatsink. And because it's a switching topology, we can use a frequency up to 1 megahertz, which means that we can make all of our magnetics and filtering external components a lot smaller. So therefore, this device is very useful for applications that require a small footprint, which, as we've seen, small footprint is becoming a real issue, a real advantage, I should say, in automotive lighting applications. So the latest device we are going to talk about is the NCV78247. This is a controller for matrix applications. So essentially the way it works is it receives the data for the pixel control parameters from a controlling ECU, control unit, and then it translates the required light pattern into individual pixel dimming info. So each pixel controller can control up to 12 pixels, and you can combine multiple controllers into a system if you need more than 12 pixels. You can organize the switches in this device in various ways. So 12 switches you can organize as a 12x1 switch array, or 6x2, or a 4x3, and so on. And other configurations are possible. And so as you can see here, that as using these as an example, the ON Semiconductor does have a broad range of controllers for these applications. And we can expect to see more as new applications arise. The last thing I want to talk about is some emerging LED technologies. Let's start with organic LEDs. This is uses a film of organic compound to produce the light. That's the electroluminescent layer. Where this compound emits light in response to electric current. You can see the structure over there on the left. The advantage of this is it can be manufactured at low cost on a flexible substrate, which of course gives it opens up large opportunities for interior designers. These displays from an OLED are going to be thin, efficient, bright, flexible, even transparent. However, this is another one of these things that have been around for several years, and if you go to the auto shows, you'll see things such as the one on the right, which is an Audi OLED vehicle, but we haven't quite seen them in production yet. They're not bright enough currently for most external use, so the initial application is expected to be such things as dashboard displays, head-up displays, and as I say, they are a couple of years away, and they've been a couple of years away for probably the last 5 years. As far as I know, no major automotive company has produced volume production of vehicles with OLED lighting. The last thing I am going to talk about today is emerging light technology. What's next for LEDs? Well, you know, nanotechnology we see a lot about that in the news, and LEDs are no different. Nanowire LEDs are promised to be the next stage in technology. Why? Well, for one thing, they can be made in an existing high-volume wafer fab, which, of course, is a huge thing for manufacturers in terms of investment. They also offer the opportunity to produce white light without using a phosphor, and the phosphor, turns out, lowers the LED efficiency by up to a third. It uses a three-dimensional light-emitting structure, and the emission area of this is up to 3 times that of a conventional LED. So we can either have a brighter LED or a lower current density. And in addition, we can manufacture multiple colors on a single chip. So that would give us an LED that naturally emits white light. You can see some of the interesting things about the structure here. It has multiple structures on a single substrate, with each one acting as an individual LED. Again, this is something looking a little bit further away. LEDs using this technology are not quite ready for volume production. I guess the bottom line for all of this is that LEDs have not stopped development. There's a lot going on that we can expect to see over the next several years. And hopefully in several years, I can issue an updated presentation that talks about some of these new developments. So you might say, well, okay, so what's the market look like for some of these growth trends? Well, this is IHS market slide showing growth trends over the next several years, the forecast going out to 2025. You can see here we divided it into three sections: high, low, and medium intensity LEDs. Broadly corresponding to high, of course, would be front headlamps. Low would be interior, and then mid would be rear lights and other non-headlamp exterior applications. And you can see here that the growth looks pretty robust, certainly in the, as you might expect, in the automotive, the headlamp part of the market, because of course those were the last ones to be developed. In fact, the growth from 2020 to 2025 for high intensity LEDs is about 35%. Low is less, 6%, but the mid ones, since we're talking about systems that are broadly already implemented, realized and so on, is essentially flat. So really, if you were an automotive developer, I would be looking at high intensity LEDs to spend your investment dollars. And of course, as we increase the amount of LEDs in vehicles, we also increase the power modules that are needed to drive them. And this is under the, broadly speaking, the body and convenience segment of the market. And this market is predicted to grow in around the 7% compound annual growth rate. But within that segment, lighting modules are expected to be the highest subsegment. You see here the LED unit growth is forecast to outpace the vehicle growth rate itself by a factor of 3. And not only that, the ASP is increasing slightly due to the higher growth rate of exterior lighting modules with respect to interior lighting. And of course, the circuits needed to drive exterior lights are more complicated because of the higher power. Therefore, you would expect the ASPs overall, the whole market, to go up at the rate greater than the market as a whole. And that concludes the presentation. And this is, of course, for mass celebration. I'm sure this included a list of resources here that you can go and look at some of the on-semi block diagrams that we saw on day 2 and click on various blocks within that to access different components that fit the application that you're interested in. So with that, thank you very much. I really appreciate your time, and I'm going to turn it over to Patrick to see if we have any questions.
Great job. Thanks, Paul. Great presentation. So grab some water and maybe take a look at some of the questions as they're coming in. We've got quite a few coming in right now. But before we continue, I'd like to maybe add a quick note to the audience. So just as a reminder, to participate in the Q&A, just type your question into the text box located to the right of the presentation window. I see some of you have done that already. Or click on the Q&A icon at the bottom of your screen and click the Submit button. So, Paul, I'm going to jump into some of the questions that we're kind of running short on time here. We have one from Maria. Can you give some examples of, or Magdalena, sorry, from Brazil? Can you give some examples of nanowire LED applications? Any come to mind?
Well, as I said, nanowires are an emerging technology that's still in the research stage. So there really aren't. They are forecast to replace LEDs in certain applications. I mean, like everything else, I would expect them to come in the low power applications, perhaps interiors, similar to LEDs themselves, interiors, and then moving to rear exterior lighting, and then moving to front lighting. But really, nobody's introduced any. It just is a broad-based technology that I think will eventually find its niche, depending on what such things as the manufacturing cost turns out to be, because all of these things are knowns at this point. It's just very promising, and as I said in the presentation, we're looking several years into the future. Right.
Okay. We might squeeze a couple more in here, but what I'm going to do is combine a couple of questions into one as best we can. So in general, some of the questions relate to the chemistry versus the driving technology. How does the chemistry relate to the driver's technology you may use? So different chemistries give different wavelengths, right? And different intensities. So how would the driver affect?
Yeah, I mean, well, you're talking about does an LED, is the current different for different? I think this is something that I'm going to have to defer to the manufacturer. I mean, as far as I know, it doesn't make a lot of difference, the current for a particular light output. I mean, the current is overwhelmingly predicated on how much light you want to have your device and subject to the maximum limit.
Right.
I don't know whether a red LED, for example, emits less current than a green LED for the same output.
I guess this gets more interesting, as you saw from yesterday's presentation. We talked about the different, almost the aesthetics of front LED design for the Audi device, right? The Audi system. It did different colors for different regions of the headlight. But anyway, so
well, yeah, I mean, it's mostly different powers, right? And so the only different color, if you remember, was the turn indicator, which is those colors are mandated by such things as some of the SE specifications we talked about before.
Okay, and maybe a quick summary of some of the things that designers should look for, or things to do to ensure reliability and longevity, right, and lower cost. So maybe, I guess you kind of touched on it with the with thermal management. I guess derating might be things.
Yeah, I mean the overwhelming thing is don't exceed the current, don't exceed the temperature, and you pay a lot of attention to getting the heat efficiently out of the unit if you generate it. And this is not unique to automotive. It's just that automotive LEDs have much higher powers than most other types of applications. Specifically, home applications. I mean, so the problems are exacerbated by that in terms of thermal management and in terms of current control and so on.
Okay. Any things that are specific to automotive then that stick out? I guess it's a very tough environment, obviously, right? So
it's a tough environment. I mean, the automotive manufacturers do not want commercial standards, which basically, fail at the drop of a hat, essentially. I mean,
right.
And even it's even after the end of production, a lot of automotive manufacturers will require assurance of supply for 20 years. So let's say, even if you discontinue the device after 10, you can't turn around and switch out components in a car in the way that you can in let's say, a smartphone. Not that I'm picking out smartphones for abuse, but you get my point. I mean, you have to develop something that's going to be around for a long, long time. And even after that model of car is no longer being produced, they still need to be able to replace components, right? I mean, at the dealership and at the repair shop. So anybody involved in the automotive business is well aware of the requirements and the investment that's needed to produce automotive quality parts, including LEDs, of course.
So talk to your supplier. It's not for the biggest thing, right?
Not for the faint of heart.
We do have to call a halt here right now, but Rick is asking how to get hold of the slides. The slides will be available online on Tech Online for some time to come, and you will get a follow-up email to track the course, so you can take it again at your leisure.
And I think we would be glad. We would be glad to forward questions on to the experts on semi, things that we didn't have time to answer here also. So
right. Good point. Yep. Thanks, Paul. So if you didn't sign up for parts 1 and 2, you can always find the link in the green resource folder to register for those. And for more information related to today's webinar, visit any of the resource links available in the green folder icon at the bottom of the screen. Within the next 24 hours, like I mentioned, you will get a personalized follow-up email with details and a link to today's presentation on demand. So again, thank you for attending part 3 of this week's course, entitled Designing with LEDs, brought to you by EETimes and On Semiconductor. This webinar is copyright 2019 by AspenCore. The presentation materials are owned by or copyrighted by EETimes. And the individual speaker, Paul Pickering in this case, is solely responsible for his content and opinions. On behalf of Paul Pickering and On Semiconductor, I'm Patrick Mannion, your moderator. Thank you for joining us today, and hope you have a wonderful week. Bye-bye.